Okay, we've got a resistor, and there's a voltage across it that varies with time. I'm going to depict that as a seat of EMF that's variable, so I'm putting an arrow through it, meaning one can change the setting. And as far as we're concerned, the setting changes automatically. We've got a resistor of 49.6 ohms. This voltage varies. I'll just call that capital V. And there's a current that results. And they want to know how much energy is converted to thermal energy during the first 8.6 seconds of operation, where with each 0.86, that's a tenth of that, so 10 times whatever that time interval is, the voltage drops to half its value, half the value at the start of the time interval. So the power during any one time interval, I'll divide the time intervals up into the first time interval, the second time interval, etc., where the first time interval goes from 0 up to time, I call it n times delta t, where delta t is equal to the 0.860 seconds. And that'll be good for any of them. So this will be the t here at end of interval. So the t here represents the time at the end of the interval. So at the end of the first interval, it'll be what it was at the start, which is 0.860. So that the voltage will be what it was. And then the second time interval goes from 0.860 up to 2 times 0.860 seconds, etc. Okay, and the deal is, during any one time interval, the energy that is converted in the resistor is the power during that time interval times the time interval. So the power keeps on dropping because the voltage drops. The power during a given time interval is the voltage during that time interval times the current that's good for that time interval. So I'll go, it's I times V, but for that particular time interval. But from Ohm's law, we know Vn, I want to get rid of the I, because we're given information on voltage, but not on the current. From Ohm's law, we know Vn, V is equal to IR, so in this case, whatever the voltage is during a particular time interval, it's going to be equal to the current through the resistor during that time interval times the resistance. So I, solving for I, this is Vn over R. And then if I substitute that in up here, I get an expression for the power that's just got the voltage in it, namely Pn is equal to Vn over R times Vn, where Pn is equal to Vn squared over R. Okay, so the energy that's converted to thermal energy during the nth time interval is the power during that nth time interval times the duration of the time interval, the 0.86 seconds. And the power during the time interval is just the voltage squared divided by R. So I think all we got to do is then add up all the energies for each of the first 10 time intervals up till 8.6 seconds, and we'll have the answer. So let's continue on with this chart. The voltage, this is, I'll call that T sub n, the time at the end of the interval. Let's go ahead and correct the spelling on that. And then V sub n is the voltage during that interval. And it will be 0. Oh, no, 236 I think it was during the first time interval. 236 during the first time interval. And then during the second time interval, it's whatever that was divided by 2. So I'll call it V sub n minus 1 slash 2. And then third time interval, it'll be half of whatever this is. So same expression. It's always the one before it divided by 2. And then the power is V squared. Power during that time interval, V sub n squared over R. That's the same for whichever time interval you're working with, now that you got what V sub R is. And then the energy converted into thermal energy during that time interval is Pn delta T. So I'll create this table in a spreadsheet, and then I just have to add all these up for the first 10 time intervals. I think will be enough to get us to 8.6 seconds. So let's switch over to the spreadsheet and copy this stuff in it. N, T, V, P, and E. I go N, T sub n, V sub n, P sub n, that's the power, and then the energy. And working in SI units, I think I'll put the units on these. This will be in seconds. This will be in volts. This will be in watts. And this will be in joules. Okay. Get all those right aligned. This goes time interval 1, 2, and then this is the time at the end of the interval will be n times delta t. Let's put a delta t up here. That was 0.86 seconds. And on here, I'll just call it dt. So this is equal to n times $A $1. Okay, and then the next one will be the same. Okay, yeah, it's doubling. And then this started out at 236. And the next one, 236, the next one is half of it. So equals the one before it slash 2. Okay, and then this equals V sub n squared over R. So that's this squared slash, I think I'll put the R right here. And I'm going to need dollar signs on it. Use absolute addressing. Really only need one, but put 2 in there. It's overkill. So I'm going to put the value of R in there, the value of the resistance of the resistor in ohms. And it's given as 49.6 ohms. 49.6 ohms. And I think I was trying to write the units in there, and I wrote a 0 instead of the symbol for ohms. The symbol for ohms is capital omega. So let's put the symbol for ohms in there. Now we got it right. 49.6 ohms. Alright, so that changed that to a value. And then this is equal to the power times the time interval, P delta T. So it'll be the power times the time interval is up here. It's $A, $1. These guys can just be copied down. Now I can copy this whole thing down. I need 10 of them. So, and that does indeed take me to 8.6 seconds. I wanted it during the first 8.60 seconds. So we're okay there. These are energies. And we see during each time interval the amount of energy converted in the resistor is smaller than it was for the one before, since the voltage is decreasing. That makes sense. So our total energy is just going to be equal to the sum of all these, sum of, and I'm just going to select them, all those guys, close parentheses. So I'm getting 1288 to 4 sig figs. That's actually 1 extra sig fig, but I'm going to write it down that way. We'll say using spreadsheet, we find E equals 1288 joules, and I think that's good to 1 extra sig fig. One way folks do that is draw a bar over the actual last significant figure, and then the bar signifies what's under it is uncertain. Well, if this is uncertain, that's certainly uncertain. So this is the first uncertain digit, counting from the left, and that would leave it as 1, 2, 3 sig figs. That's our answer. As far as showing your work, don't forget to print the spreadsheet.